Hello everyone, welcome to one more session of live discussion. Today, topic of discussion is photonic chips versus semiconductor chips. Today, I welcome Mr. Ashwini Kumar Sinha and Suresh Dwivedi ji for this discussion. My first question is, how does the design flow differ between photonic integrated circuits and traditional semiconductor ICs?
Yeah, can you repeat question again?
Yes. How does the design flow differ between a photonic integrated circuit and a traditional semiconductor IC?
Yeah, yeah. So photonic semiconductor based any kind of device or IC or processors are now very are now very uh, in developing stage, and a lots of people are doing research on that, and they're quite different in terms of both working model and in terms of the manufacturing part. Both are very quite different, and process are very different than the one in the semiconductor and one in the photonic waste. Okay, so in photonic semiconductor based design or IC or processors, one thing we have to deal with the light. They are photonic, the photons. We are dealing with the photons, the light one. Okay, so to design such photonic based any kind of photonic based processors device or design, we have to uh, put effort, and we have to do we have to take what say we have to take consideration of various different aspect of that the whole process. So one is the waveguide design and optimization. Okay, so that you can ensure the efficient light and its propagation is done in very efficient way, a very efficient way, and there should be minimum loss of optical loss. What optical loss? So there are various kind of optical loss happen when you design such kind of photonic based devices or photonic based the processors and many other such devices. So one of the because of this certain lightning effect, certain characteristic and properties that light carry. So as you already have heard or already know that the light can be absorbed based on the colors, based on the material, the reflectability change, the scattering of light, the coupling of light, the polarization of light, the absorptions of light, all these make effect on that. So these are all what you consider these. These are all the optical loss. So when the light gets scattered, there is optical loss. There is a loss in the overall light that we're transmitting. And in photonic chips or in photonic processors, what we need to transfer the light. So the certain certain circuits, photonic circuit that we have made, like the photonic transistor, photonic diode, whatever the things. It's not completely in manufacturing stage, but a lot of people are developing and try to do the R&D. So we are talking about that thing. Okay. And then one of the other thing is the polarization of light. Light can be polarized based on the various conditions, based on the various other things. So that is another challenge. And then the thermal and environment compensation and the electro-optic inference management. So there are various different aspect of that that you need to consider in terms of the photonic. While in semiconductor, uh, electronic chips, it's different. The case is different. So in the semiconductor, you have to talk about the impedance matching, and then the power integrity. You have to talk about you have to see about the thermal dissipation. You have to think about the electromagnetic interface, EMI. Most of the device need the EMI shielding in that. So that's the another aspect for this. So so both of the this is how the both of the things in design and manufacturing side we have to consider two different things, because there are both very different way of and very different things. One is the photonic chips that works on the light. One is the electronic chip that works on the electronic signal, electronic power supply. So one uses the light to process, other uses power. But in semiconductor, we have a lots of development, and we are already using most of our devices. In fact, all of the devices are using the semiconductors. Currently, there are very few photonic chips and very photonic, but still it's in development bit. And once it develop, it's one of the best things that we have to do, because as we all know, there are few advantages that light based chips give you, light based processor give you. One is the in one is the uh, uh, it didn't matter how much your device get warmed or heat up, the environmental factors, the heat around the that didn't affect. While in semiconductor, if the device get too much heat, then there is a degradation in chip, and also there is thermal throttling in overall performance. We face the thermal throttling in the overall performance, cause a lot of uh, 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 a lot of problem in performance of the device and optimized performance of the device. Okay, but in light, it's independent of that thing. And second thing, light travel with the speed of very one of the fastest speed that we yet know. I don't know, there are many some other waves, I don't know who knows. So that might be faster, but till now what we know, that what we told, what we read, and what we have discovered, and till now, that one of the fastest things is the light wave. It's one of the fastest traveling waves is the light waves. Okay, so it's the fastest. So anything that process with the use of light with the photonic chips, they are very fast. So this is the one advantage of these things. Okay, so both have its own advantage and disadvantage, and while manufacturing it, both of the we have to consider the different aspect for that.
Okay, so what are the key layout constraints when designing waveguides and photonic chips versus routing metal interconnection electronic chips?
Actually, designing waveguides in the photonic chips involves a distinct set of the layout constraint compared to the routing metal interconnection in the electronics chip, primarily due to the different physical principles governing optical versus electrical signal transmission. In electronics chip, metal interconnects carry electrical signals and are typically routed based on the resistance, capacitance, and the inductance constraints. Designing aim to minimize parasitic effect, ensure signal integrity, and the meet timing requirement. The routing can involve sharp corners, wires, and the multiple metal layers without significantly degrading the performance, as long as design rules like minimum spacing and the width are followed. Conversely, photonic waveguides, light, and their layout must preserve optical mode integrity, minimize losses, and avoid reflections or scattering. One of the most critical constraints in the photonic design is the minimum bend radius. Unlike metal traces, waveguides cannot make sharp turns. Doing so can lead to significant optical loss. Therefore, bends must be gradual to ensure that the light remains confined with the waveguide. So, spacing between the waveguides is another key constraint due to the convenced fields around waveguides. Placing them too close can cause unwanted coupling or crosstalk. So, designers must maintain sufficient spacing to avoid the signal degradation or unintended interference. Another parameter is the tempering and the alignment are also very crucial. Transitions between the different waveguides widths are types. For example, from a strip to a rib waveguides must be carefully tempered to the minimum mode mismatch and the insertion loss. Precise alignment is essential, especially for coupling light between the component like laser, modulators, and the detectors. So, additionally, waveguides are the often confined to the specific layer with the strict material and the thickness requirement. And they require optical DRC rules that check for the optical performance constraint rather than the just manufacturing. So in brief, overall we can say that the waveguide design in the photonic requires a deeper consideration of the physical optics, which imposes unique constraints that are the absent in the standard metal routing. That's all.
Okay, so what are the challenges of co-packaging or co-designing photonic and electronic components on same die or substrate?
Yeah, yeah. So there are lots of challenges when you do these things and like co-packaging on the same die, the photonics and electronics. But first, let's understand why do we need it? Because most of the device, as I've told you, the LCD to the everything are electronics and they work on the electronics way. So if I have the photonic chip, I have the photonic processors. But at the end of they uh, at in part they might sending the signal to then display something on the LCD or giving some kind of output. Then that photonic whole process, after doing whole process, that have to be transferred using the signal. And those are the electrical signals, because at the end of the day it has to be, because we haven't yet developed the whole photonic motherboard, whole photonic working device. It's just in development phase. So at the end of the day, even we are using the photonic chip, we are using the photonic processor. At the end of the day, you have to it has to be, it has to be the electrical signals to, to go give you some kind of output in form of LCD display or total calculated number, whatever the things is. Okay. So, what we are currently doing, we are currently using the photonic based processors or photonic based chips, photonic based IC, combining them with electronics. And when we want to do that, we have to think about the die. We have to coexisting both of the photonic part and the electronic part both into the same die. And when you do the whole things in the same die, when you want to do package the whole photonic chips and the electronic components in the same die, we have to want to manufacture it in the same package. Then a lot of problem, a lot of challenges you face. And now let's talk about the challenges. So yeah, so the challenges, one of the challenges uh, is the thermal management, because uh, electronic electronic part, I've already told you that create a lots of dissipation. The heat, it got dissipated from the electronics part, and they need to be managed, because that heat dissipation from that electronic part can be in some way disrupt the other, uh, disrupt the substrate or disrupt the photonic uh, part on the die. Okay. So that is the one of the things. Second is the layout. The photonic component are generally larger, and so they reduce the area remains for the electronics part. So that is another challenge. And then and then each the another one is the fabrication. They are incompatible in process of like of replacing both things on the same die. uh, they're incompatible. The coexisting of the same design is very hard to do, make it compatible with each other. Okay. So that is another thing. And then there is a testing part can be also very crucial for that. Like mixed signal validation requires specialized setups and to test that whole things out, whatever you're going to manufacture, what you're going to do. And so set up these things, it's another. And then one of the most important and important challenge that you face is even after the validation of your area, that is the design level, because there are very less amount of tools or EDA tools or sometimes tool that enables you to do those designs, the both things design in the same die for the same die, very expensive, because the photonic chips and all those photonic processors are still in the development phase, and the electronics are still are semiconductors. EDA design tools are different. Okay, and when we're going to combine manufacturing and going to put in the same substrate, then we need another tool to that has the capability to analyze both design rules, both design things. So it's very complicated for you to get the tools and design your own tools for doing these things. Okay, and yeah. So these are the things. There are few challenges. There are more challenges are there, but they are very deep. If I tell you that will take a lot of time me to explain that. So I'm just leaving all those things because they are so in depth. If you go in the depth of the whole die design.
Okay, so how do thermal design consideration differ between photonic chips and semiconductor chips? Suresh sir, you are on mute.
Sorry. When we are talking about the thermal design, so actually thermal design consideration for the photonic chips differ from those of the traditional semiconductor electronic chips due to the distinct behavior of the optical comparison. For example, thermal sensitivity of the optical properties, it is also very important. In photonic devices, rely on the precise optical behavior such as refractive index and the resonance wavelength, which are the highly temperature dependent. Even small temperature variation can shift the performance of the components like ring resonator or the Mach Zehner interferometer electronic chip, while affecting by the temperature are the generally more tolerant to small thermal fluctuations. Another sensitivity parameter is the wavelength stability. Maintaining a wavelength stability in photonic system is very crucial, especially in the dense wavelength division multiplexing DWDM. Temperature changes can cause wavelength drift, impacting signal integrity. So, as a result, photonic chips often require localized thermal tuning or the control element, such as the heaters or the thermoelectronic coolers, adding complexity to the thermal design. Next parameter is which is the localized heating. It is also playing a important role in photonic chip. May include active elements like laser or the modulator that generates significant localized heat. Managing these hot spots without affecting nearby thermally sensitive passive components is challenging. In contrast, electronic chips have more uniform heating distribution, and the thermal management focuses on the overall heat removal. Next parameter, which is the packaging constraint. Photonic packaging material and the structure must not only dissipate heat effectively, but it also preserve precise optical alignment, which can be disrupted by the thermal expansion. Semiconductors packaging focuses primarily on the minimizing thermal resistance and maintaining the electrical performance. Next parameter is the cooling strategies, it is also playing very important role. While electronic chip often rely on bulk cooling method, such as the heat sink, fans, liquid cooling, etc. But in photonic chip may require more targeted thermal management to stabilize specific optical components, making thermal design more intricate. So, in brief, uh, while both chip type require thermal management, photonic chips demand more precise thermal control to maintain optical performance management, localized heating, and the ensures wavelength stability. Challenges that go beyond the needs of the standard semiconductor chips.
Okay, so when designing for high-speed data transfer, what key trade-off must you consider between electronic and photonic paths?
Yeah, what can you repeat it?
Yes, yes. When designing for high-speed data transfer, what key trade-off must you consider between electronic and photonic paths?
Yeah. So for designing high-speed data requires a careful consideration of whether use electrical signaling or the copper or silicon interconnects, or the or the photonic, that is the optical signaling through the waveguides or the fiber optics underlying between the PCB, or whatever the things that we're going to use that, or or the underlying path for the light, and the combination of both. So each approach has a unique advantage and limitation, and the choice involves the navigation key trade-offs like bandwidth, the latency, the power consumption, the distance, the cost, the integration, complexity, and the reliability. So there are many various aspects of that where you can look on that, and then uh, uh, then see its depth of it. Okay, so let's consider the electronic path. Then you have the for the semiconductors, there is high bandwidth short distance like 1 Gbps per lane is PM for modern thing. So yeah, so for the high speed data transfer, if you using the electrical path for that, then uh, electronic signal is not one of the fastest way to do that, to transfer the data, because light is more faster than that in opticals. And and the signal strength, but when you transfer the signal for the longer distance, then every wire poses some kind of resistance. Okay, so if the longer the path, the longer the signal loss is there. So you might have seen there in the in your electrical cables, or the the broadband cables, after every few poles, you see the device, an amplifier kind of device, a big kind of device. What its work is to amplify the signal, because the signal and the electrical strength, everything got degraded with the decreased with the length. Okay, because of the resistance in the wire and many other factors. And after a certain, its signal is very weak, and that can't be even so it has to be amplified. And then at a certain, so after certain level, you need some kind of remodulation or amplification at a certain level, and also the bandwidth, the data transfer becomes slow in electrical part. But when you go for the optics one, then it's travels with the speed of light. Okay, so when it's travels the speed, it's the optimum thing. It's at optimum, it's the most efficient way. And while doing this, there is no resistance, there is no electrical resistance in light. There is no resistance, just fiber optics. You just light it up and at lightning speed it get transferred. Okay, but in that case also, if there is a breakdown in the fiber, the whole signal get lost, or managing the fiber optics a little bit also complex. Okay, and so these are the another consideration of the fiber optics part, for when you're using it for the for the data transfer. So in fiber optics part, the data transfer is very fast, but at the same and it didn't depend on the length. No matter how much larger the length is, the speed didn't got decreased because of the length. But managing the fiber optics, they can be the, you can't bend it too much. The wires can't be too much, and the wires need to be managed properly, because they can, if they got damaged, because these fiber optics in the optical wave data transfer, it depends on the total internal reflection. So the light get enter, and it internally gets reflected, and that's why you get at the other end. So if you bend it too much, if the wires got bent too much or got damaged, and the total internal reflection got disturbed, then the data transfer didn't happen after the at the time where at the point where it get broken. So that is one of the key challenges, and that is one of the drawbacks of that, for the optical part, fiber optics or optical based data transfer, high speed data transfer. But if you ignore that, the optical bit high speed, for the high speed data transfer, opticals are very best. That's why we use the optical fibers. But in case of the electronics, the semiconductors based, like if you're using electronical signals to transfer the data, at the every particular length, the signal got decreased, and the internal resistance wire got also, uh, heated up, and you also need a more thicker wire to get to avoid, to get the electricity passed easily, and also, uh, uh, there are various factors for doing that. Okay, so both had its own advantage and disadvantage, but for the highest speed of data transfer, and for a greater bandwidth, the fiber optics and the optical part will give you the more bandwidth and highest speed in terms of the other things. Okay. I don't know I will able to give you the answer that you are asking for or not. So yeah, as far as I understand the question, I've just given the answer. Yeah. So yeah.
So what process node compatibility issue arise when trying to fabricate photonic components using standard CMOS foundries?
Just actually fabricating photonics component using standard CMOS foundries presents several process node compatibility challenges due to the fundamental differences between the electronics and the photonic device requirement. A primary issue lies in the materialistic standard CMOS process are optimized for the electrical performance, often using silicon with thin top silicon layers and shallow edge depth, which are not ideal for the photonic structure like waveguides, which requires thicker silicon layer for the effective optical confinement. Another key issue is the lack of the appropriate doping and the etching profiles for the photonic devices. Actually, photonic components such as the modulator and the detectors often requires custom doping, concentration, and junction placement that deviate from the CMOS design rules. Additionally, photonic devices may require deep trenches or specific geometries incompatible with the shallow CMOS edge depths. And the wavelength compatibility also poses a challenge. CMOS foundries operate at the electrical design rules, and the materials suited for the sub-nanometer lithography, while the photonics typically use larger feature sizes. This mismatch can lead to the inefficiencies in the layout and the design of the translations. So, moreover, the process of the metal layers in CMOS can introduce optical losses if not properly isolated from the photonic region. So, optical components are the sensitive to scattering and the absorption. So, materials and the layer placement that are the acceptable in the electronics can degrade photonic performance. Thermal budget during back-end processing also impact the photonics. High temperature steps used in the CMOS process can damage previously fabricated photonic layer or degrade the optical performance through stress and the material diffusion. So, in the last, we can say that the standard CMOS design kits like photonic PDKs, process design kits, which complicates integration without dedication. Photonic design rules, circuit simulation, and the mass generation for the photonics are the error prone and the time consuming. So overall, to overcome these challenges, foundries offering photonic compatible CMOS processor such as the silicon photonic platform have emerged, offering modified processor that retain CMOS compatibility while supporting photonic components fabrication.
Okay. So, what simulation tools or methodologies can be used for photonic versus electronic chip design?
Yeah. So if we compare for the photonic versus electronic simulation tools and the methodologies, then if we go for the photonic chip design, there is a physics part for that. For the photonic chip design is is optical. That is what we call Maxwell's equations. So we have to calculate it according to that. And in the electronic chip design, we have to go for the electrical laws like the Kirchhoff's law and all those things. Okay. And at the and for the design and simulation tools available for both of the different designs, one is the synopsis opt sims, that for the simulation of photonics and optical device designs. I can spell it out: SYNOPSYSOPTSIM. So synopsis opt sim. Okay. And then if you go for the electrical design, there are lots of out there like VCS, Mentor, or Open Road, or and like Cadence, and also Synopsys VCS. So these are the different circuit level tools for the different design, like for the photonics and for the electronic chip. So one of the common company that you find here is the Synopsys SYNOPSYS. That is Synopsys VCS for the electronic chip design, and the photonic is the Synopsys OptiSim, OPTSIM. Okay. And if you go for the system level, then you can get the for the electronic chip design, electronic circuit. You can get the MATLAB, Simulink, Cadence. Or if you go for the optical thing, then you can get OptiSystem, the Synopsys Opto Designer, and the MATLAB. Okay. And if you go for the physical part, like the physical analysis, there are there or the layout tools for the photonic chip design or the electronic chip design. Then there is a Synopsys Opto Designer or the Cadence for photonics. And for the electronic chip design, it's the Cadence and also Synopsys IC compiler. Okay. So for the semiconductor, it's the Synopsys IC compiler, Cadence, or for the photonic chip design, it's the Synopsys Opto Designer or Cadence photonics. So Cadence are in both sides, you can see, but it's just different versions of that. One is for the optical and other is for the electronics. Okay. And if you go for the verification tools, then there are like K layout and for the photonic chip. Okay, and for the electronic part, we call it synopsis IC validators and something. There are a few more. I'm not taking the all of them name. It's let's go for the next. Okay, so these are the things. Okay, uh, for that. Okay, so so if you go for the tools ecosystems, then Synopsys Opto Designer are specialized and less integrated and require manual workflow uh, for the photonic one. But if you go for the same for the electronics, uh, it's specialized, and you don't need to do much kind of manual work. There are lots of automations are there. There are lots of easy, they made it easy to build because it's being used for since a long time, and lots of development had happened in that part. But in the photonics, it's just a starting page, so it's very, there are lots of manual work we need to do. Okay, and so these are the things. Okay, so these are the things.
Okay, so what are the major performance bottlenecks if you have that you can encounter in photonic chip design?
Yeah, so in photonic chip design, there are lots of bottlenecks are there. I have already told you that one is the what say, if you transferring the if you're designing the photonic chips, then you need a light to be transferred, and for the better performance and for the better reliability, you need a lasers, and if you go for the lasers, if you need a very high high performing lasers, then they are very expensive. The cost one is the one of the key challenges, and then its efficiencies like uh, 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 per channel, they consumes 10 to 100 milliwatt per channel. uh, uh, so so that is 20% more than the what the silicon offers. So that is one of the power consumption because of the laser part, not the whole chips, because once you emit the light, and this the whole process thing are done based on the light. But at the initial level, you need to emit the light, and for the emitting that light, you need the laser, you need the laser diode. And for the bit, for different wavelengths, for the different need purpose, the different kind of laser with a different type of power consumption and different wavelengths and different specifications. So that's the another thing. Okay, second is the thermal effect of the thermal impact. Okay, on the uh, with the increase of the thermal, the reflective indexes changes sometimes. So that might be the problem. Okay, and second is the what we call the signal degradation, or we call it wavelength drift, because of the thermal. They are the optical, most of the optical devices are or optical parts used there are thermal sensitivity. They suffers the wavelength drift based on the thermal. And in the electrical, we go for the silicon, they also have some problem based on the thermal. Because of the thermal, they you faced the what's the uh, thermal throttling, or the because of the heat. Okay, and heat dissipation from the electronics part. So both have this problem, if you say. Okay, and in case of the power, you need high end lasers and very tuning and drivers, you need theirs. And sometimes you also need the prism filter, color filtration, and many other parts are also there to be there. And okay, and then the optical losses, in case of the optical part, there is a lots of optical losses due to the various uh, 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 various process in the design. Okay, so these are the things for both of the thing. Okay, the optical and the semiconductor.
Okay, so how can you verify timing and synchronization when mixing electronic and photonic signals on the same board or package?
Actually, verifying timing and the synchronization in system that mix electronic and photonic signals is a complex but critical task, especially as data rates and the integration level increase, because photonic signal travels at the speed of light in the medium, and the electronic signal have slower propagation and the response time. Precise coordination between the two domains is essential to ensure reliable system behavior. At the design stage, when uh, we use co-simulation tools that integrate both electronic and the photonic models to analyze signal propagation delays, jitter, and the skew across the entire system. These simulations help identify critical timing paths and determine latency mismatches between the electronics drivers and the photonic modulators, or between the photodetectors and the electronic receivers. In the clock domain synchronization, it is typically handled using high-speed phase-locked loops (PLLs) or the clock data recovery (CDR) circuits in the electronic domain. We ensure these circuits are tightly integrated with the photonic interference, especially when dealing with the serial optical link. For time critical applications, we align the photonics modulation windows with the electronic clock cycles using programmable delay lines or tunable optical delays. Timing calibration is also essential during testing and the packaging. We use we normally use built-in self-test BIST features and time domain reflectometry TDR to measure actual signal delays and adjust accordingly. In high-density photonics electronic packets, temperature variation can cause timing drift. So we include thermal sensors and the implement adaptive tuning mechanism like thermal tuning of the ring resonator to maintain timing alignment. For system using VWDM, we verify that each wavelength channel is synchronized properly, particularly when different channels are routed through the different optical paths. Synchronization is the vertical, synchronization is verified using eye diagram analysis, bit error rate testing, BERT, and the real-time oscilloscope. Ultimately, robust timing verification is the biggest electronic photonic system requires a combination of precise simulation, calibration, and the adaptive control mechanism to maintain synchronization across the high-speed interference.
So, which applications have clear performance advantages from photonic design approach versus electronics?
Yeah. One second. Yeah. So can you repeat the question?
Yes, yes. Okay, so which applications have clear performance advantages from photonic design approach versus electronics?
So one of the one of the good application that photonics have the advantage over the what's the what we call the versus the electronics. Okay, is the data transfer in the optical data transfer at the work with the light speed. So it's very high in the optical. You will get very high rate of data transfer like 400 Gbps or 1.6 Tbps per second. And if you go for the bandwidth, like light have lots of different bandwidth, so we can add different bandwidth of light for the different data transfer. So there are different bandwidth. Per bandwidth, you can divide the whole data. So it can reach up to 400 Gbps to 1.6 Tbps per module via wavelength division, what we call the WDM. Okay, wavelength division multiplexing. Okay, this is what we call. So you will get a larger bandwidth in the photonics and also very high rate of data transfer and distance loss over the distance. Like I've already told you that if there is a wire, if it's electrical wire. So if in the electrical wire, at every distance, at every distance, uh, there is some electrical loss. There is a big due to the resistance in the wire, the internal resistance in the wire cause some electrical signal loss. Okay, so with every distance, increase in the distance, the signal got weakened, and there is a loss in electrical power as well, and power got dissipated with the resistance in from the heat of in the wire. So in the electrical, there is a loss over the distance, where in the fiber optics it's very less. It's very less. It can keep it negligible. So this is suppose that this is one of the fiber optics that we have. Suppose that. Okay. So uh, it totally work on the internal reflection. It has the fiber. It's a glass fiber inside these things. Okay, and we have here the input of for the light. You can see here we have the input for the light here. So all I need to just put the uh, uh, put the laser in front of this end, and the light got transferred to the this end at the very lightning speed. And while doing all this process, it's totally working on the radiation, that is light travels in the form of radiation. So as it radiates, as it and work on the total internal reflection capability of the light. So light got internally reflected and then reach to the other here in the fiber optics. So in the whole process, there is no resistance caused by the uh, due to the distance. So no matter how long this wire is, it can be this short. It travel with the same speed without any loss. If either it at this speed it travel with the same speed without much loss. Even at this speed, if it travel, so no matter how much longer the wire got, it's between the one city or between the one country to the two country. If we connect two countries with the fiber optics, the the losses due to the distance in fiber optics very negligible. So so this is one of best advantage: the bandwidth, the speed, and the loss over the distance. While that the electrical part lacks a lot.
Okay, so as a design engineer, what limitations of current photonic integration platform would you want to resolve in the next generation?
Yeah, so as a design engineer, there are lots of limitations in integrating the platforms that I want to resolve. It's what say uh, one of the let me think of the resolution, because there are lots of challenges are there. So as a design engineer currently, as a researcher also, as a design engineer, I am doing research and working on various kind of things. So currently we are not totally working on the photonics things. Like we have the photonic processor, then it has to give the signal in the end. That's why we need the both photonic and electronic coexisting and co-coupling in the same die or same manufacturing. So we have to combine both of them. So currently we are not totally photonic. We are not, there is a lack of total photonic based transistor, that mm, there is a lack of total light based motherboard, where not only the processing is processing with on the lightning speed with using the photonic chip, but whole electrical circuitry who get replaced by these photonics. So you have the photonic diode, you have the photonic transistor, you have the photonic what's a inductor. I don't know how we can make it, but this is one thing that I want to make. We have to change the discrete component also in the electrical motherboard and change it the photonics, and in the in the in the layer of this, that the PCB, Instead of the tracks of the wires, the copper wires or the aluminum tracks, we have the tracks of the optical layers that I want to do. Yeah, and not me. There are a lot of people are out there who want to do, and that is what I'm also doing some research on that.
Okay, so my last question are, how do design verification and DRC or LVS process for photonics differ from traditional semiconductor flows?
Yeah. Uh, Actually, design verification and the DRC LVS processor for the photonics significantly differ from the traditional semiconductor flows due to the unique nature of the photonic components and their interaction with the light. While traditional semiconductor verification focuses on the electrical properties such as the connectivity and the device functionality, photonic verification must also consider optical behavior, something not typically addressed in the conventional electronic design automation EDA tools. In traditional flows, design rule checking (DRC) ensures that layout geometries comply with the foundry specific rules to guarantee manufacturability, and the layout versus schematic (LVS) check that the physical layout matches the circuit's schematic netlist. These processes are mature and highly automated for the electronic components like transistors, resistors, and the interconnectors. However, photonics introduces challenges such as the waveguide bends, mismatches, and the optical losses, factors that are not captured by the standard DRC or LVS tools. For instance, a layout that possesses electronic DRC could still perform poorly optically due to the tight waveguide bands or the improper tempering. Thus, photonic DRC involves additional check like minimum bend radius, waveguide is specific to the avoid cross checks, and optical continuity, often requiring custom rules, checks, and the specialized tools. Similarly, in case of photonic LVS goes beyond the verifying connectivity, since many photonic devices do not have straightforward schematic representations. So LVS for the photonic often relies on the netlist extraction using optical aware engines or the hierarchical matching of the parameterized cells, P cells. This is the further complicated by the hybrid nature of the photonic electronics integrated circuit EPICs, requiring co-simulation and the co-verification strategy. So overall, while the foundation of the DRC or LVS remain photonic, demands new methodologies and the tooling emerging platform now integrate photonic aware check and the simulation models, enabling more accurate and the reliable verification. So the shift reflects the broader move towards the heterogeneous integration, where the photonic electronics and the even MEMS coexistence necessities in a rethinking of the traditional verification flows to embrace optical and the multi-domain constraints. These are the factors.
Okay, so this brings us to the end of the live session. And if you have any question, you can put it in the comment section. Thank you for